Yesterday, the idea of solving the differential equation was about getting to a specific result. I do not expect you to be able to solve the second order differential equation thing by guessing. Guessing was just a means to prove something to you and give you two pieces of information I did want you to have. The first, you should be able to take the derivative of sine or cosine with the information presented yesterday. So if I present you with a function that has sine or cosine, you should be able to take its derivative. We should work at the next part of this, which is you should look closely at it and figure out what the antiderivative would look like under those circumstances. So this is the generic. It should work for any oscillator or any system in which this differential equation is produced. We had a specific answer in that our differential equation was based on the spring mass oscillator, which gave us something that looked like this. Right? We didn't just have this, we derived this from Newton's second law. But this is what we got as a result of looking at Newton's second law. So I'm telling you right now, for any situation in which you're going to have to see if something is a harmonic oscillator, you will start with Newton's second law. Now, I don't believe I have to do all of this, but hear me out. Net force equaled ma. Step one, the applied force was that of a spring. We substituted in the definition of the acceleration in terms of velocity. We subbed in the definition of velocity in terms of position. We wrote this a little different and isolated the differential. Right, those were the set of steps that got us to this differential equation. This is our generic differential equation. And that's what we did yesterday. So we're all up to date now? So the first thing I want to do is apply that to the spring mass oscillator. We know from what we just looked at that the spring mass oscillator has a value for C that is equal to the square root of K over M. That's just from looking at that relationship and seeing where the constant is. Now, what that does is create a set of motion equations that are about the spring mass oscillator and aren't generic. I want to look at just one of them for a moment, and we're going to look at each one of them separately because there's something important from each. Instead of C, I'm going to put in square root of K over M times T. Implication number one, because I don't think you guys see the small stuff. So my first implication. Without doing any work, the units of the square root of K over M have to be radians per second. They have to be. Everything inside here has to be in radians. We are multiplying our constant times a time. So the units have to be radians per second. You should prove that. The units for the spring constant are newtons per meter, and the units for mass are kilograms. You should prove that that works out to be something or nothings per second. It's the only way this works. That's why, implication number two, the square root of K over M is often called the angular frequency, because it's in radians per second. I defined oscillatory frequency for you already. I said the oscillatory frequency is in oscillations per second, but this is an angular frequency. And everybody who's had a little bit of pre-calc and has done the little waveforms knows that this term inside your cosine determines whether the wavy things are close together or far apart. That's what that term does. That's why it's called a frequency. Next, how long until this system repeats? What does that term have to be for the system to repeat? It has to be 2 pi. When it repeats, the time it takes for the system to repeat is called the period. So when the square root of k over m is equal to 2 pi, the system has repeated. We call this the period. That means that the period is 2 pi times the square root of m over k for a spring mass oscillator. That also means the period is 2 pi divided by c, or 2 pi divided by omega for the generic oscillator. This is in your equation sheet. And it has some obvious things in it that you should look for. It takes longer for objects with more inertia to oscillate, right? M is in the numerator. So if I put a bigger mass on the spring, the period will be a bigger number. Do you see it clearly? And it will oscillate faster with a stronger spring. That's why K is in the denominator. I said from the very beginning, if asked questions about the period, inertia makes things oscillate slower, and the restoring force makes things oscillate faster. Frequency is the inverse of the period. Notice it's omega divided by 2 pi. That's converting radians to oscillations. That's why it's there. We know these two are related. That's the first implication. So I want to go on to the next implication. All good? The velocity function. I'm going to replace the c with the square root of k over m. Do you see that the sine value can only be a number between 1 and -1? So we know that this is just scaling the value. But the biggest that number can be is 1 or -1. Does that make sense? This is the velocity. So when sine is equal to 1, this must be the biggest the velocity can be. Clear enough? Do I need to say that again so you can get it in your notes? Sine is always a value that is between -1 and 1. So the biggest the number part can be is -1 or 1. This part is what we multiply sine by. And we know that's got to be in radians per second times whatever x naught is. So for this problem, it's meters per second. Since 1 is the biggest sine can be, our maximum velocity has got to be the square root of k over m times x naught. That's got to be the fastest the oscillator can go. Now, look at your picture for a spring mass oscillator, the one that shows it oscillating back and forth. Do you have that available to you? Back here, this is not a surprise. I want to do one more thing. It's a little more challenging. Bear with me, okay? I want to take a look. So, one half m, this is v. Squared. Plus 1/2 k, This is X. For a spring mass oscillator, at any moment in its oscillation, this should be the total energy. With some of the energy in the form of kinetic and some of the energy in the form of potential. 1/2 m. This is going to be c squared x naught squared sine squared ct. Everybody okay with all that? You understand but the square on the sine, what it looks like? This is going to be 1/2 k x naught squared cosine squared ct. It looks really messy, but remember, this is c. So that's k over m. Do you notice on the left side the m cancels out there? So I'll get 1/2 k x naught squared times sine squared ct plus 1/2 k x naught squared times cosine squared ct. This term and this term are the same. They can be factored out. I'm left with sine squared ct plus cosine squared ct. And everybody in calculus should know this, and I think some of you in pre-calc should know this. What is sine squared plus cosine squared? It's 1. This is proof that the total energy of a harmonic oscillator is conserved, that it stays the same no matter what point in the motion we are. The total energy is always going to be equal to the amount of energy we gave the system at the beginning. Just more evidence that these represent our motion equations and that they fit the properties of a harmonic oscillator. So once you give a harmonic oscillator energy, that energy stays with the system. Now, here's why I spend so much time talking about this generic state. I want to prove something else to you. I want to show you something else. I want to show you how to use this. Before I show you how to use this, though, I need you to prove something to yourselves, and there's only one way to do this. You'll need your calculator. We're going to do this fast, so you need to work quickly, okay? I'm going to put up, let's see, there's 8 tables. So each table's getting one of these, okay? So we'll start with 1, 2, 5, let's go, 3, 5, 10, 15, 4, 5, 6, 20, and 30. These are all in degrees. Okay. I want you to convert these to radians and then take their sign. I don't care whether your calculator is in radians or degrees, but you might want to make sure you are careful about doing that. I want this to 4 decimal places and this to 4 decimal places. So here we go. I'm assigning each table, starting over here. You guys are 1, 2, 3, 5, 10, 15, 20, 30, okay? Each table has one of them. So convert it to radians and find the sign. And the approximation says this, that for small angles, theta almost equals sine theta. It's called a small angle approximation. You may not understand why we need it, but we need it. Are you sufficiently convinced that this is true? Where's the cutoff? You understand that there really isn't a cutoff. It just becomes less true the bigger the angle is. Do you guys see that okay? I want you to keep that in mind for what we're going to do next, the small angle approximation. I want to show you why this thing, all of it works. I'm going to write this down again. Keep it to the side and understand its implications. We know that a simple pendulum oscillates, right? Simple pendulum. We want to show if it is a simple harmonic oscillator. For it to be a simple harmonic oscillator, it has to fit this pattern. So we need to study it. I'm going to suggest we study it using torque and not study it using force, but you could study it either way. It's just much easier to use torque. Is that okay? So I will move it because if I don't, I found in this class, too many of you are susceptible to suggestion. 7th period, it's almost pervious to it, just so you know, but you guys are unable to tear your eyes off of it. It's a little bit weird. A simple pendulum. And when we say a simple pendulum, we say that the system has no inertia given by the connecting rod, and that all the mass is considered a point mass that's concentrated at the bottom. That's a simple pendulum. So I'm going to consider a simple pendulum which has a pivot point here, a length of string or rod or something that's massless, L, and the pendulum itself has mass M. I want to see if we can put together a differential equation that could be used to show if this is a simple oscillator or not. I want to talk about it from the net point of torque, but you could do force, but like I said, torque works easier. Besides, we have to do the physical pendulum next, and it's torque, and it's just easier to see it done once this way. So if you'll recall, this is a point mass. There's no inertia given by the thing that's holding it. So our moment of inertia will be ml squared times alpha. Okay? There are two forces acting on the pendulum. Can you name them? Gravity. Excellent. Gravity acting this direction. And what else? Tension. Do either of them cause a torque? Which one? I don't think tension does. Look at the direction of tension. If the torque arm is the distance from the pivot point to here, wrong color. If this is the torque arm, won't the angle of the tension be 0 degrees? So there'll be no torque from the tension. All right, what else possibly?
Sometimes.
I think gravity does. I think gravity causes a torque. And you said sometimes, you're right. When it's straight up and down, it doesn't. Straight up and down suggests the net force is 0. That sounds like equilibrium. And I also see a system in which the force is getting bigger because this angle is getting bigger. Wouldn't you guys agree? I didn't say it was an oscillator yet, but I'm starting to see qualities of an oscillator. Moreover, if theta is measured in the positive direction this way, won't the torque be in the negative direction? Using my right-hand rule, it's into the board to rotate this way, but the torque is causing it to go out of the board that way. So the torque appears to be in the opposite direction of the displacement. All sound good? Let's write out what the torque is. Torques are a torque arm times a force times the sine of an angle. And I'm pretty sure this angle is also theta, just based on all corresponding angles. So my torque arm length, L, my force, mg, my angle, sine theta. I can clean this up a little bit. First, I can cancel out the M. I can cancel out one of the L's. And I'm left with alpha equals G over L sine theta. And measured from theta, the restoring force is negative. Now, my recollection is alpha is d omega dt, and omega is d theta dt. Right? Motion equation stuff from kinematics. They'll behave just like the motion variables. So I can replace alpha with d omega dt. And I can replace omega with d theta dt. Negative G over L sine theta equals d squared theta dt squared. Wow, that looks a lot like this, doesn't it? Pretty close, aren't they? Maybe if I keep the angle small, I could get rid of the sign. If I keep the angle small. If I do that, then this must be related to C, right? In fact, C, which is angular frequency, must be the square root of G over L. It must be. What does that mean? It means the period of oscillation of a pendulum must be 2 pi divided by C, or 2 pi times the square root of L over G. It means the frequency has to be C divided by 2 pi, or 1 over 2 pi times the square root of G over L. Tells me the motion equation for a oscillator is going to have to be theta equals theta max times the cosine of the square root of G over L times T. That the speed will have to be equal to square root of G over L times theta max times the sine, square root of G over L times T. I don't need to reprove it. I've proved it once for this. I can just apply all of these principles. The most important principle that you get out of this is to be able to come up with the period and frequency of the oscillator. It is the most important. It's the thing that is asked the most. How do these things control the time? And I know I said to you that it's going to be inertia divided by weight. Do you see that it's inertia divided by weight? Remember, the inertia is point mass, ml squared. I know there's only an L in the numerator here, but weight is mg. So they're there. If I put an m here and an m here, do you see it now? Why they show up there? It's just that the result, because gravity is also part of the inertia here, the mass. It causes gravity and is also part of the inertia. That's why the mass cancels out. So we're left with the last and most important thing about inertia, the distribution of the mass. And G, what causes it to oscillate. Now, I know this is a lot to take, but if you can make a differential equation that looks like this, that controls how the thing oscillates. There's a 1 in 10 chance you're going to be asked to do this on the exam. 1 in 10. If it shows up, they're probably going to give you the answers. If you look in your equation sheet, you have 2 of them already. The spring mass oscillator and the pendulum are already there.
Good morning. We are through.
What do you want the period of oscillation of your clock to be? That would be a pretty big pendulum. I think probably there's a smaller time increment that I would like the pendulum to swing at. So you'd have to decide what's reasonable. Do you want it to swing once every minute? Once every second? Once every hour? What's the increment that you wish to tell time in? What do you think is reasonable? I'm thinking seconds is probably reasonable. Minutes seems weird because although I would like it to be a minute, try it for both. You guys think I'm doing this in the box. This is the kind of stuff I'm expecting you to be able to do, and you're looking at me like I'm crazy. But if I put in 1 second and set that equal to 2 pi times the root of L over G, you should be able to tell me how long the string has to be. And for the person who said we should have a minute, give it a try. So if I gave you a pop quiz tomorrow asking these things, I'm expecting this would be easy. You'll see why we make clocks one way and not the other. We'll end there. All right, so looking at this picture, this part is equilibrium. Where that red line is, this is maximum displacement. At this moment, the velocity was equal to 0, which means all of the energy was in the form of elastic potential energy. These things conserve energy, so when it made it to here, it's moving, right? It's at equilibrium, the net force is 0, this is V max. I know you're gonna ignore this. That's one of the things that they play on the AP exam, knowing that at this moment, the net force is 0. So equilibrium is a critical point in an oscillator. Be aware, you will often have to find it. It's not always obvious where it is. It's not obvious on this one that's just oscillating up and down. Equilibrium, the relaxed position of the spring changes depending on where the weight is and how much weight you're using. So be aware, equilibrium is an important point because it says net force is 0 at equilibrium. That means the acceleration is 0 at equilibrium. V max has got to be 1/2 mv squared, not V max, K max has got to be 1/2 mv max squared. All of this energy has now been converted to this energy. If I set those equal to each other, get rid of the 1/2 and solve for V max, we get what the motion equations predicted, right? It's the exact same thing. It has to work out this way because the energy, the motion equations have to demonstrate conservation of energy. So if I look at this point in the object's motion, the energy right here. During this time, the object is somewhere in the middle of its motion. Right? It's somewhere in the middle of its motion. So it has a little bit of kinetic energy and a little bit of potential energy. Does that make sense? So if I wanted to know how much energy the system had at this moment, I know it should equal the amount we started with. It should, right? Because energy is conserved.